identify all the objects that are in the system. So that's going to be the cart, the earth, the track, and the spring. So what's happening here? We got a spring that's going to launch a roller coaster cart from rest on a frictionless track, and it's going to go into a vertical loop-de-loop type thing. Okay? So important stuff here. It tells us that it starts from rest, and it tells us this track is frictionless. Cart starts from rest. All right. So if it's starting from rest, Josh, how much energy is stored in its motion when it's at rest? Zero. So to indicate there's no injury stored in the motion, I'm just going to put an X there through EK. How about gravitational interaction? Hayden, if it falls on you at position A, is it going to hurt you? It's already on the ground, right? Yeah. So we're just going to put an X there through the EG. It doesn't have the potential to fall any further, so that's not happening. All right. Ayana, how about springs or rubber bands? Are there any compressed or stretched springs or rubber bands today? Yeah, right? That's what this thing is. So that's where the injury is stored. This spring is compressed at A, so we're going to have some EE. How many blocks you thinking? 2? Okay, thanks for not saying 28. So we're going to have 2 blocks there. All right. Position B. So look at what's going on at position B. Chase, does it look like there's the potential for getting hurt by this thing if it smacks into you?
Yeah.
How do you know that? It's moving, right? We got those little lines there, so it's moving. All right, how much EK should it have? I'm asking you, how many blocks? 3. All right. Maggie Towler, if it fell on you from position B, would it hurt you?
Yeah.
Okay. How many blocks? 2. Suguladze, are there any stretched or compressed springs at point B? Not anymore. So that's going to be an X for that one. 80. Did friction store any of this energy in this problem thermally? Why not? Frictionless. Okay. So I'm going to put a big old X right there. Now, translate this to the video we watched in the back. 28 blocks in the beginning, 28 blocks in the end. 2 blocks in the beginning, 5 blocks in the end. What's the problem? That math doesn't work out. So what do we got to do? Either put some more blocks here or take some blocks away here, yeah? So the number choice is arbitrary. You could have 4, you could have 10 to start with. You just need to have the same amount before and after. So I can fit 2 more here. So for that reason, let's make that be 4. And then what do I have to do on the other side? Yeah, you got to get rid of 1. All right. So this last step then is just writing an equation that says how everything is stored. So it's E at A, and it's going to become EK at B plus EG at B. And that's it, right? You guys can handle this math. This is going to be a reasonable quiz whenever we get to have one. All right. Oops. So then we're going to repeat this problem for a frictionless system that includes the cart, the earth, and the track, but not the spring. So the only things that what'd I do? Yes. Yeah, sorry. So kind of the same thing. When energy gets dissipated, it could be thermal, it could be sound, it could be just vibration. And we kind of throw those all under the blanket of dissipation. So I should have specified that. So this is like thermal or sound or vibration. Could even be light, potentially, okay? But those are all forms of the energy getting dissipated, getting kind of spread around. All right. So when I'm stocking up the bedroom here, I've got the cart, I've got the earth, I've got the track, but I do not have the spring involved anymore, okay? So Spence, at position A, is there any injury stored in the motion of the object? Why not? It's not moving. It's not moving, so I'm going to put an X through there. All right. PB, is it going to fall on us and hurt us at position A? No, it's on the ground, so I'm going to put an X through there, okay? The cart, the earth, the track, do those things have any elastic injury stored in them? They don't. So I have no blocks here at position A. Now, everything else about this problem is the same. So if in the previous problem we said that at B, there are 2 blocks of injury stored in the motion, there are still 2 blocks of injury stored there. 2 blocks of gravitational interaction injury, yeah, those are still there. So this is that problem with there are no blocks in the bedroom initially, but now there are blocks, okay? You didn't have the, oh gosh, I don't know, what toy did you covet when you were a child? The Lego Death Star, but now all of a sudden you have it? How the heck did that happen? Okay, oh, your friend brought it over and they left it, okay? So that's what's going on here. Now these blocks have been left behind, but they had to get into the room from somewhere else. And so that somewhere else is a thing called working, which is just to say how the energy gets into the system. Working.
Can we draw it like that?
Yeah. So it's a block arrow. You know, like the block arrow? It's kind of cool. Okay, so it's a 4-block arrow. I guess I don't want to write that right there, do I? I'll write that here. It's coming from the spring, and it's working into the system. And so when I write the expression here, I would just say W spring, and that equals the EK at position B plus the EG at position B. Nothing really fundamentally has changed about the problem. If you're watching this, 1B looks exactly like 1A. It's going just as fast at B as it was in A, and it's just as far up the loop in B as it was in A. This is just sort of an accounting practice, if you will. All right. 1C, it's the same thing as 1A, but now there's friction. So same thing as A, we're going to have the cart, we're going to have the earth, we're going to have the track, we're going to have the spring. But now there's friction. So think about how a track that has a little more friction is going to affect what we see. Same thing as 1A. So, oops, why am I putting it in EK? That'd be silly. It's not moving. It's not at a greater elevation. So I'm going to put in 4 blocks at position A. In EE, it's stored elastically. Don't think about energy for a second. Just think about the fact that there's some friction. When it gets to the top of the loop, what would you say would be different if there was now some friction? If we had used a cheaper cart, check with your neighbor. What would be different about it?
What would be different? There's EK. There's EG.
All right. What's going to be different about it? We use a crappier cart that's got some friction with the track. What's going to be different about it if you're watching it? Cart's going to be what? A little slower. It's still moving, but it's slower. If it's slower, that's our excuse to say there's less energy stored in the motion. How much less? One less. All right, so I'm going to have one block of EK. Could I have one block of EG? Why not? It's still the same height. There's still just as much danger stored in the potential for it to fall on you. So I'm still saying 2 blocks there. Block in the spring? Nah, right? We already said there's no more compressed or stretched springs, so that's not present. So this is where we're going to introduce dissipation. All right? Friction took some of that injury that was in the motion of the cart and caused it to heat up the track. Or maybe it made a lot of noise. Maybe it made a scraping sound. Okay? So now I have E at A, and it's equal to EK at B, EG at B, and E dis at B. So some important things to understand about dissipation, okay? When that energy that was the motion of that jet or the motion of your car gets stored thermally by friction, you tend to not get that energy back into other useful forms, okay? It's just kind of heating everything up, okay? This is not a root cause of global warming, but your car's going 70 miles an hour and you bring it to a stop, all that potential for injury that was represented by the motion of the car is now stored in an increased temperature for the brake discs, okay? If you're dumb like me, you look at that brake disc, and it's kind of shiny, and I like to touch shiny things, so I did that once. My brakes were making a weird noise, and so I was worried like maybe the face of the brake disc is rough or something, so I thought I would touch it. No, it's not rough, it's just really freaking hot, okay? And hot metal tends to look a lot like cold metal. So don't touch it was like the kid with the bicycle there, poured the water on it and it got steamy. Yeah. There's a lot of potential for injury in a car going 70 miles an hour. And now if that car is stopped all of a sudden and all that potential for injury is stored in the increased temperature of the brake discs, they're going to be really, really hot, okay? A lot of potential for injury there, get blistering. The thing about that is, though, that once you store it thermally, you tend to not get it back out. So I liken it to the Carlos O'Kelly's gift card of energy storage, okay? So my neighbor lady, I do nice things for her, like I do the snow blow in the driveway or whatever, or mow the grass. And I wouldn't let her pay me, but then every once in a while she'd throw me like a gift card. And it would be like a Carlos O'Kelly's gift card. And like, I don't know about you, but like I don't see getting a massive bout of diarrhea as a reward for doing hard work for something. So I'm not gonna go, OPD work. Okay, fair enough. I mean, like maybe I'm gonna go get some chips and salsa, but I'll be damned if I'm gonna go get like a Fiesta sampler, right? So she might put $30 in that gift card, but I'm only gonna get like $10 back out of it. I'd rather have some other form of money storage than a Carlos O'Kelly's gift card. That's what thermal injury is like. You might put Dodge Durango going 70 miles per hour worth of injury into heating up those brake calipers, but you're not going to get that back out, okay? It's uncommon for you to get much useful injury out of thermal. So, for example, this kilogram, if I give it a push here, there was some potential for injury stored in its motion. Okay, but yeah, let's check this out here. You ready? Feel it.
It's the same.
Okay, it's a little warmer. So the table got a little bit warmer. That thing's not moving now. The injury that was stored in its motion is now a little bit of sound. You can see we actually did hurt the table there a little bit. But the table's a little warmer, okay? I applied for a foundation grant to get a thermal imaging camera because I wanted to do that. Like if you stuff your feet across the floor or you skid a bike tire, you'll see an increased temperature there with the thermal imaging camera. But unfortunately, I didn't get it. I see biology got some electrophoresis gel plate things, I think. And Sheila got some ergo meters or something like that. So I think I'm probably not getting that thermal imaging camera, damn it. But there's a warm track on that table, I assure you. You can see an infrared. It would not violate conservation of energy for that thing to start moving and the table get colder, right? The energy would come from the table. It was stored thermally in the table. Now that thing has got it stored in its motion. The table is colder by the correct amount. That wouldn't violate conservation of energy. It'd be weird as hell, though, if all of a sudden chairs started moving and the room got frosty, right? You'd freak out. You'd probably pee a little bit. It'd be kind of scary. It doesn't work that way. There's some other laws that are at play here from thermodynamics that prevent that from happening, okay? So it's not purely conservation of energy. There are some other rules at play here, and we'll talk a little bit about them more later, okay? So next week, is there a 1D? Dang it, there's a 1D. All right, we'll pick up with that stuff and hit the ground running on Monday.